Okay, welcome back for our final invited talk in MFPS. Very nice to be allowed to or be invited to introduce Ohad. Ohad has a Royal Society Research Fellowship holding in Edinburgh, but he spent quite some time here in Oxford. And I think this talk is on a synthesis of these ideas that he has worked on and picked up Edinburgh and Cambridge, I believe, and also Denmark and Oxford in particular. Please, Ohad.
Thank you. It's a pleasure and an honor to be here. Thank you for the chairs for the invitation. Yeah, so this is MFPS. So we're going to focus on the foundations rather than the programs, but I think I should start by trying to contextualize this. Okay, so this is about semantic foundations, right? So statistical and probabilistic modeling. Okay, so what I mean by statistical and probabilistic modeling, okay, if you have some distribution, this is try to keep it completely neutral, age versus the time you go to bed, and you try to define some kind of distribution on it, and if you were born on the moon or something, you have no clue what to do. Everyone goes to bed about the same time, maybe 10 p.m. or something like that. Okay, but then you actually look at what's happening, and you get a slightly different distribution that incorporates the data into account, right? So maybe teenagers and students go to bed really early in the morning, and old people like me go to bed really early at night. Okay, so that's the kind of the point of probabilistic modeling. You want to kind of define these distributions and then ask all kinds of questions on them. What do you look at after you incorporate the data? What is the measure or the probability of the area under the surface and so on? And the other questions you want to ask in statistics. We want to sample from this, generate a random time that the 40-year-old go to bed. Okay, great. But this is MFPS, so let's think about the programs coming to it. And this is an old perspective that's got some kind of recent tailwind. And this is probabilistic modeling as programming. Okay, so if you have a program that does some process, then probability distributions describe the behavior of programs. Okay, so distribution describes programs. But you can flip this and think the first papers in our community are Saib Jorobi from 37, Dexter Cawthon from 78. Say, let's flip this. Okay, let's use programs, sophisticated programs, all the tools that you might write to scale up programs to describe sophisticated distributions. Okay, so we can, you can write something like this or close to this as part of our model. Okay. So what does that look like in maybe more closer to practice? Okay, so you have a lot of the language, say simple data calculus plus some sampling construct is equal something, and then you can add other programming features to scale it up, like data types, recursion, polymorphism, just add your favorite feature, right? That would be a way of describing a sophisticated sampler. You might want to describe sophisticated models, Bayesian models. So that means you're not only describing kind of your prior sample, the one on the left. Okay, you're also describing how the data that you collected or that you're trying to model fits into it to get the picture on the right. Okay. So concretely, that looks like you have a sampling construct, but then you have some observation construct that manipulates density, like we saw in the beginning. I think there's really interesting questions there. Big Part has a recent paper talking about constructs for observation. I think there's still semantic questions. Okay, and of course there's a whole bunch of maybe benefits or maybe properties that the programming language perspective adds to this. Okay, so you can have more sophisticated modeling via more advanced field programming language features or via more advanced statistical components. So I think one of the mostly used probabilistic programming languages is STAN, and most of its users, which I think are numbered at hundreds of thousands, don't even know they use it, because some library in R calls a STAN component. Okay. So kind of you bring in it off the shelf and something sophisticated under the hood. Inference can be sophisticated. Sam Staten is he in the room? Hello. There's a neat language called lazy people that uses laziness both as a sampler, but also as the part of the inference. And systems, right? When you're using a, a programming language off the shelf, maybe not, maybe a domain-specific one, it's probably going to be a bit better than the one you knock off in an afternoon, right, by yourself. So the system you use might be more scalable, more efficient, more convenient to the experts. That's the promise, whether that's the reality. Hopefully, it's the hope. Okay, so I think from this point, we're just going to go drill down the foundations. Okay, so it's just a context. There's a lot of people much more fit to talk about the previous two slides, but we can also take that offline and talk about that. Fine, let's just really focus about the maths here. Okay, so if you don't think about the maths, it's good to set up what we need. Okay, so what kind of maths, what do we need for the maths? So we do need some notions. When I say space, I mean the thing we'll be distributing over. So for the first slide, that's going to be the bottom bit. Right? The thing we're going to have a probability distribution for. Okay, so we definitely want to have things like Boolean because these are like outcomes of a coin toss or success or failure of some binary trial. Maybe some kind of a finite spaces, right? So we want to have things like categorical distributions, but maybe the day of the week that something happens, or maybe they roll the dice. Okay. Well, infinite domains, for example, the count, how many buttons arrive per hour, for example. Integers, maybe priority in some kind of potentially unbound queue. Okay, rationals, maybe timestamps, because they can arrive out of order, and so on. Continuous spaces, right? Why continuity? That can be philosophical, so let's not go there. But maybe even just practical. When something is continuous, it's amenable to a whole bunch of optimization techniques, right? So if somehow the signal gets infinitely small and kind of permeates through the whole domain, and you can use it to solve problems that are very, very hard otherwise. So let's always say optimization, but also, our current epistemological position is continuous spaces that's the thing we do when we use. Okay? So the reals, intervals for times, if they loop. Scaling factors can be even infinite, and probabilities, like between 0 and 1, inclusive. Okay, so we definitely want to have those. We want to have random positions, hours, scaling factors, probabilities, and we want to put things together, so combinators. Okay, so definitely products, for example, we have two correlated outcomes. Co-products, which I'm not going to talk about today. We want to say, for example, either I have a coordinate because I'm in the field somewhere, or I'm in one of a given location. Right? So that's going to be either a discrete one or a previous position, for example. You want to have subspaces that impose maybe semantic invariants with all possible outcomes are correct. So think about, say, the two-dimensional sphere inside a space, for example. Not all points are relevant for the modular sphere. That's a subspace. And quotients, like bags. Swaraj here, I think you work on point processes, which are distributions over, over bags. Great. So that's the kind of stuff we want. What else do we want? We want to measure the probability of events, right? That's Kolmogorov's innovation is to use events as a foundation probability. For example, we look at the set of outcomes of a dice about 3. Okay. So the foundation for that is going to be measure, probability measure that takes it for every event, assigns to it a probability. We're going to use this notation, the probability that a point sample from you is in the event, satisfied with the output. And if you have never seen this before, then I will cover it in the next slide. If you have, then you should all be familiar, and then you should feel like a fuzzy feeling of treading along a familiar garden path. Okay. So what are the axioms for probability, right? So probability is total in the sense that if you have nothing, that has 0 outcome. If you want a partiality, you have to model it explicitly by adding some kind of partiality point. Disjoint events have additive probability. That's the second axiom. And continuity. I have a sequence of events that are all increasing, right? And the probability of the limit, the least upper bound, is the limit of the probabilities. Okay, and the main probability is that the probability of the whole space is 1. Okay, so that's a probability measure. If you've never seen that, now you have. There's nothing more to it than this. Almost. Okay, so here's the almost. This is the almost as early as measure theory was discovered, right? And a few years later, this thing came to be, which is that if you assume the axiom of the choice, then you cannot assign a measure to the real line that extends length. Okay, and it's a translation invariant. So if you move an event around, its measure doesn't change. Okay. It's a 3-page paper, I think, so you can go and read it. I think you have to read the translation unless you speak the native language. I think it's French. Okay. So what do we do? Okay, we have to work around it. The traditional way is to take the very least of RL sets, right? So we'll say in a second what they are, but you can of course get more and more sets that you can assign probability to, but you can never get all of them. Okay, so the ones we definitely want in the classical story is if you have two events, you can take the finite intersection, finite union, and an empty event, full event. We need these axioms to even phrase the axiom of probability. Okay. And the one to deal with continuity, you have a chain of events that you need to be able to take the least up around. Okay. And we will store in the lengths, and now this is kind of the minimal family of subsets we should be to measure to even phrase this theorem. Okay, and these are the Borel sets, and maybe you can try to measure more of them. Okay, and of course, then Vitali was an answer to a question that came in earlier, is that there is a unique measure that assigns to every Borel set a number, satisfies the axioms for measures, each translation invariant, and measure lengths. Again, you can extend it a bit more than just the Borel sets, but we'll stick there. That's called the Lebesgue measure, the unique one. Okay, so if you kind of restrict yourself to say 0, 1, it's going to be the probability 0 1 uniform. Right. Okay, so then what the classical story does, we take the situation of being closed under the finite set theoretic operations and limits, stop limits, and that's called a sigma field of subsets. Okay, we kind of base all our spaces based on kind of the worst case of the Borel sets. In the Borel sets case, we can do better. So we say every space now is as bad as the reals. I'm being a bit naughty. Okay, so these two axioms. So if you have a set of points, we define a sigma field to be a family of subsets. Those are the finite set theoretic operations, union countable union sections. And a measurable function is a function whose inverse image sends these events in the target space to events in the source space. That's the usual story. That's all there is to it. Actually, not going to do that much measure theory today because we'll get it in a second. So here's the first typo. It promise there will be typos. Probability space is a measurable space equipped with probability image. So it sums up to. Okay, and this is pretty good for as a modeling foundation because we get all the basic desiderata, right? So we get discrete spaces, we get continuous spaces, we get ways to put things together like products, subspaces, coproducts, and quotients. All of these are fine. Even measures for the space, that's great. Okay, but they're not so good for a programming language semantics foundation. That's also famous for the almost for the beginning. Alman, who wanted to do some game theoretic modeling, and very quickly got to this question and talk a bit more about this offline. So take the space of measurable functions from the reals. Now let's try to turn it into a measurable space. So pick any sigma field, okay, any collection of events that's putative. Okay, whatever you choose, the evaluation function is not going to be measured. That's like the first node of theory, very old, very hard to fabricate this. And really, what's bringing it a bit earlier, the products are kind of what stops you from getting there. Because once you choose this the sigma field, then this space is kind of determined through the product combinator, and that just ends up being bad. But if you go read the paper, it's very nice. Right? You read it from left to right. You get to see the construction. It's very pretty. And language talk actually cover the proof in 3.7. But they only had an hour. Okay, so let's just take the consequences of this. So no go for event spaces if you want to talk about random events, that's out. And no go for pi types if you want to say dependent types. Neil is not here, he would be disappointed. No go for functional programming, no go for object-oriented programming. Although, if you really buy into having programs describing distributions, you need to go somewhere else or do something else. So coming up with semantics for development, that's a long tradition in MFPS. I listed a few people. The slides are on Discord, so you can read it. I'm really sorry if I missed you. Definitely missed lots of people. And this is just the probabilistic powder ones, so there's lots of other parties here. We can spend an hour just talking about that. But what's exciting in the last few years, maybe 6, right, is people have been chasing up the semantics for higher probability and continuous distributions. So this is coming from the reals. And we had a slew of papers from the last few years trying all kinds of ways around it, all kinds of universes in which you can do probability and continuous spaces and have these more spaces, things like function spaces. And some of them are really nice. I've learned about the one from Alex 2 weeks ago in his talk. That's what we organized, thank you. Which really just goes out the window, which is pretty nice. Today I'm going to talk about one kind of model. And it's almost an invitation for people to try to tell a very similar story with one of these other models. Okay, so I really took the model we worked on, which is the quasi-Borel space, and tried to run with it as a foundation for probability, and not in many others. Okay, great. So what is this quasi-Borel spaces? So Sam is here. Came up with them. I want to say just up there, because Sam's office is up there, my office was up there, but I think you committed that from home, so we bought at home working. I worked in the library. There's lots of libraries in Oxford. You can be in the summer underground, in the winter you can hide somewhere and get some work done. Okay, so these quasi-Borel spaces, the kind of the basic premise is very well, let's say straightforward. Okay, so this on the left we have the usual story, and on the right I put away quasi-Borel space theory. So on the left, what we have space of point, that's the donut, the torus. And over it, we define what are the signal field of events. Okay, we start with the events, these are the things you want to measure. That's the primitive notion. And out of it, we derive what's called the random elements, the random variables, the ways in which we can map a probability from probability space omega onto our space A. And they are based on axioms, and we never gave them names, so I just had to call them metaphorology. Okay, because I'll tell you later. Okay, that's good. So now let's just flip it. Okay, I'll tell you in a second what the metaphorology axioms are. But what we have is a set of points and a metaphorology on it. And out of this, you can derive a sigma field of events. And the rest of the theory you can continue developing it. Not quite the same way, but not that differently. So if I gave this talk 7 years ago, I would then have to start doing something with these spaces. I'd have to give you evidence that you can do something with these quasi-Borel spaces. For example, maybe prove some theory of probability, like the definitive theorem, or maybe verify some Bayesian inference implementations, or design some probabilistic programming languages. Maybe invent a new one to do with networking, or formalize it all in a theorem prover to show that it's formalizable, that it's all correct. Maybe verify cost analysis, or maybe even do something crazier that Sam and Dario did, which is use them as a model for danger duration. Okay, instead of gensimming, you just sample a uniformly distributed number, and that's your new name. And of course, the reason I say this is because I don't have to do it, because it's already been done. We can go and chase the references, okay, and that's not going to be this kind of talk actually. Okay, you can see talks for all of those things, especially in the age of remote conferencing or hybrid conferencing. Everything is online. Go and see them. This is all fascinating stuff. Instead, what I'm going to do is I'm going to give you a little mini tutorial. Why? Because it's very rare that I get so many semanticists in one room as a almost captive audience. Okay, and you might think that to get all of these results, I have to do something really complicated with these quasi-Borel spaces. And the real secret is that it's quite straightforward. So actually, it's going to be like a minute tutorial what it's like to work with them, try to convince you, if not to do something with them, maybe, do some exercises, give to your students. So I'm working on a course. Okay, there's lots of exercises there. It's only half finished. Okay, but if you want to get into it, please go ahead and inevitably you're going to find some mistakes. Inevitably, they're going to be bad. They're going to waste your time. Apologies in advance, but please let me know so that they don't waste anyone else's time. Also, I'm here. Sorry, we are, have a PhD program in Edinburgh. Alex was there as a PhD student. I was there as a PhD student. William was there as a PhD student. I'm probably going to miss someone else. Sorry, but apologies if I missed you. This is the LFCS one, and we also have a brand new CDT with robotics, really exciting for dependable AI. We're closed for this year, for this one, for the coming year. This is still open, actually. So if you really, really want to apply, come to me. Okay, but that's the only slide with advertisement. Sorry. Okay, so the theme for today, in fact, it's only going to be the first one. And we're going to use types. So you're going to use the fact that quasi-world spaces have more types floating around, okay, to abstract over measurability. So Alex, in his atomic shift universe, can get rid of measurability completely. This universe does not, but it can hide it better. Okay. And the advantage is that moving from working inside the universe to outside, so from the internal language to the external functions, is actually quite smooth. It's the main difference that working in the shift topos. And what I'm not going to do too much today is use types to organize probability concepts. So apologies. I did front load a little bit of probability, not the best probability, but just a little bit, just so you can see some of it. But that's why we have all these other papers. So it's really going to be about measurability, how to find measurability. And the reason I do it today in this forum is, unless you're trying to really push the foundations of probability, what you're doing is trying to reason about probability to do semantics for like a probabilistic programming language with extra stuff. Okay. Then this is actually a pretty good universe to be in. Okay, so I'm trying to encourage you to, instead of going through measurable spaces and everything is a no-go, everything you have to check, here everything is actually much easier. And if it's not, tell me. Yeah. Or Sam, or your local quasi-world space expert. If you write it in the paper, then we can say it's another problem, right? That's pretty good, right? Okay. What I'm not going to do today, I'm not going to talk about the column structure of quasi-world spaces, apologies, and that involves a big chunk of probability. So I'm sorry about that, but as I said, there's a course, there's papers, there's talks. I'm not going to talk about dependent types. Unfortunately, I do have a lot to say. And I'm not going to talk about random variable spaces and stochastic processes, also because Alex tells me better ways of saying it. So I'm kind of also being self-serving here. So that's pretty good. But the course does talk a bit more about it. So you can go and check that out. Oh, you're standing. There's a problem? I'm showing the screen. Oh dear. Okay. The slides are available on the Discord. I did post them, so you can follow that. I'm not sure what else to do. You can follow through the video. The video works, right? They can see the video. Oh, they can see me. They can't see me even. Oh my! Can they hear me?
Should I do something?
Please do something. That's okay. 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 You can? Thank you. I'm really sorry for those at home. This is the slide I'm in. I'm going to give you 5 seconds to catch up. No. Just to get to this slide. You haven't missed anything important. I don't give it any definition, right? Just story. Okay. So let's just jump in. What's a metaphorology? Okay. So I have a set of points, the donut. And metaphorology is a collection, a family, R, big curly R, of functions from the reals into X, and we think of them as ways of pushing a probability on the states. The 3 closure axioms. The first one is constants are random elements. Okay, the function that's always getting the same value, okay, that's a random element. Second one is going to be called precomposition on the next slide. And the last one is recombination of the last slide. This is just 3 axioms. Okay, great. Second one is precomposition. So what does it say? I have a random element, alpha, and a well measurable function, phi. And I precompose alpha with phi to get something of the right type. The axiom says it's a random element. And maybe I should say something about this. We're going to have to deal with the Borel sets, whatever we do, right? Because we want them. We want them, we don't want to change the universe more. So what we're doing is we're taking the best case and we're generalizing from it. All right, we're only dealing with measurable functions from the reals of the reals. This is the case where probability theory works really well, right, in continuous spaces. We have Borel measurable functions from the reals of the reals. Okay, and the last one is recombination. So this is, I have my space, I chop it up into a countable collection of Borel sets again Borel sets. Each one of them has a random element, and I glue them together to get another element. I'm going to use this notation of square brackets, of coupling, right, maps together. What this axiom is saying is I can decompose the reals into the disjoint union, the coproduct. This is kind of the pattern matching on the coproduct. Used to this if you're doing functional programming. Usually there it's fine. If it's infinite, it's also difficult. And that's it. Yeah, that's a metaphorology, and the quasi-Borel space is a set with a metaphorology unit, and that's that. Okay. Maybe I'll take questions.
The anthropology of metaphorology.
Yes.
Yeah, same question.
Okay, then. In Greek, meta is across. It was Alex. You correct me. Across. For is transfer, I think. So I'm transferring across things.
And it's an element.
Yes, it's a collection of things that can transfer probability across. So yeah, that tends to call the metaphors rather than other elements, but I will not do that. But you can if you want to. Yes.
There are ways to understand this as like the invariant categorical terms, something like a cheat.
That's for you. You can read. Yes. Question.
Yeah, could you explain what a random element is again? I don't.
It's axiomatized. So I have a collection of functions from the reals
How do I think about it?
as a measurable function from the reals into the space. Okay. So all the top of stairs in the room has read this, so I can just carry on. Don't even have to mention it. Okay. Very good. Nick, did you understand it? Yeah. So you can go and ask Nick later. Okay. No, I'm being a bit tongue in cheek here. You know, the new upfront is going to have all the right properties. What I think we didn't quite know is how much right properties it's going to have. So that comes up with chasing the structure to its conclusion. I think even Alex was surprised at some of the results we have in this moment. I think he's smiling. Maybe he's not surprised. Anyway. Yeah. But I mean, it doesn't need to be surprising. It just needs to work, really. Yeah. Anyway, I'm not going to dig myself deeper into this. Very good. So let's look at an example. You should always look at examples. Okay. So I think something about the part is full of examples. Thank you. Let's take the reals, right? How do we turn the reals into a quasi-Borel space? We take the points to be the real points. Apologies for the abuse of notation, and the random elements are the measurable functions from the reals into it. Is that okay? That gives you a bit more intuition. Great. You can generalize if you have any measurable space, you can do the same construction. So you have to prove that it satisfies the metaphorology axioms, but it does. It's not that difficult. It's one of the first few exercises I said in my course. Let's look at another example. Let's look at the minimal collection of the minimal metaphorology. Okay, so what's a sigma symbol function? It's a recombination of constants, right? So when I write it like this, it's clear that every metaphorology is going to contain all the sigma symbol functions. So if you have any set, I can equate with the it's a discrete metaphorology, and that ends up being a quasi-Borel space. So now I have a copy of set theory operating inside quasi-Borel spaces. In fact, I have another copy. By doing the opposite, it's a closure condition. So I just take the maximum one. That's the indiscrete one. And if CB is listening, no, it's not cohesive. Apologies. That's why I asked my question yesterday. We can talk about that thing. Sorry, that was a side chat out for CB. Talk about cohesion in the context of polymorphism and parametricity. Okay. So what's a morphism of quasi-polar spaces? It's a function of the points that preserve the random elements. It's another right condition, it goes forward. So if I had random element alpha, plus composing it with the function gives you another random element, and that's a morphism of quasi-polar spaces. Let's look at some examples. Every constant function is a morphism of quasi-polar spaces because plus composing with a constant gives you a constant. That's an easy proof. Not all the proofs are this easy, but they're not that complicated. It's nice. Okay. Great. So saying quasi-polar space morphism is a mouthful, so I'm just going to call them measurable. Okay. Apart from this case. Okay, if I have two measurable spaces and a measurable function between them, I can turn them into quasi-polar spaces, and then that function is also measurable between them, but that's confusing. So that's the only case I'm going to call it quasi-measurable. Anywhere else, I'm going to call it measurable, because it doesn't matter. Great. So now we have a category because identity, right, is a morphism, and composition of morphism is a morphism. So we have this situation. And like Andy, I get limits and collimate because it generates them. It doesn't create them, but it does generate them, which means it takes and preserves. So quasi-polar spaces have limits and collimates. I'm not going to talk about collimates today, just about limits. And I'm going to explore this space, this consequences of limit structure in detail. Once more, just because maybe to prevent another question, I have these adjoints floating around, so actually I can move between measurable space and quasi-polar space. It's very fruitful, but we can get there. Yes?
On the previous slide, when you said it creates these limits, was that the composite or each one individually?
No, just the bottom one.
Oh.
This one, and because there's a left adjoint, it preserves limits. Yeah. This one preserves coproducts. Okay. So I told you what metaphorologies are in quasi-polar spaces are. That's the first part of the talk. In the rest, I'm going to talk about the simple type structure. That's really the limit structure. And I might get to standard spaces, might not. But that's okay, because this is really going to be a tutorial for you to see what it's like under the hood, rather than teach you all the theory. For that, you can talk to me, invite me. I'm happy to come and talk. It's a couple of books. Great. Okay, so let's start looking at those space combinators. This is just the limit structure. So if I have two quasi-polar spaces, the product is a metaphorology structure over the Cartesian product of the points. That's the nice bit. And what's given is given as a random element in the product is a pair of correlated random elements. So you have a random element in the first component and the second one, and they operate together. In the projections of the set-periodic projections, the tupling are the set-periodic tupling, and that's the point of preserving limits, right? It's all what you think it is. And that lets us talk about, say, products of the reals, even infinite ones, only the binary case we can do arbitrary ones, definitely one, not hiding anything. And measure theory can do this, can do as much. You can talk about addition, multiplication being measurable, taking infima and suprema. The limit superior, limit inferior, and so on. Okay, so what can you do with this? This is not much, but you can already do quite a lot. In fact, I think that's the bread and butter of what you can do. You can interpret the first order simple type theory. There's nothing, I really didn't put anything here. Okay, but really most of the work that you do is there. Right? So if you can express the function you're defining in this language, it's measurable just by looking at it. You might be running a fact checker on it, but it's just measurable. And problems, once they get past the ML syntax, they're happy. If you want, you can put it in JavaScript syntax or any other syntax, Python syntax. That doesn't matter. Right? It's the structure. And the point of this semantic universe is that it's very smooth to internalize and externalize. Okay, there's these terms. If you think of them as functions, they are those functions more or less. Maybe up to some semantic invariants floating around, but more or less, they really are the same in the syntax and the semantics. And that's really, really powerful. Okay, so that was the first order. Yes, you could do in measure theory. That's not different. Difference comes in the next step. Okay, so let's look at function spaces. Okay, so what's the function space from x to y? So this is y to the x. The points are the quasi-Borel space morphism from x to y. What else would you want? Yes. And the methodology is going to be uncarrying the quasi-Borel space morphisms from R times x. But what else would you want? Okay.
Sorry.
Yes. Sorry, that's another typo. Yes. Thank you. Inverse recovery. Sorry about that. And evaluation ends up being measurable. And I had a slide comparing with measure. Okay, so if you're wondering why that happens, suspend for 5 slides. And that gives you simple type theory, simply type number calculus. And that's giving even more oomph, right, for writing program, because now I can abstract and apply, and that's really, this is how you write modular code. You can talk about object, you can talk about functions. That does not matter. Having the ability to have functions is the important bit. Okay, so here's an example that you can't really do in measure theory, not so easily, right? It's taking the limit superior of functions. You have to be careful what I mean by that. I mean pointwise. Okay, so given a sequence of functions, you can take the function that's pointwise the limit superior. That comes up when you say, well, give a measurable version of a martingale or something like that. And it's taking a function, right? This is not a measurable space. Okay, its measure depends on a function. It's something that's inherent to this theory. Can't do it in theory. You have to do something else to replace it. People do. Very often you just wait until you go back to the first order, then you have a lump of functions to prove measurable. Okay, here you don't need to. The building block is measurable. It's really powerful. What else can you do with it? So the simple example, let's look at a slightly more nicer example, random element space. Okay, so I have my random elements, but I can turn them into a space. Okay, so there's a space R X, so the same kind of font, but now it's not just a set, it's a quasi-Borel space, and its points are the random elements. And it's given by the exponential, so x to the r ends up internalizing the quasi-Borel space structure. And I have the proof here, but I actually will not go through it. You can look through it on the slides. But what can you do with it? Here's a little example. It's not the best example, it's just a short example, but I can talk about probability earlier on. Okay, so let's look at Riemann status integrals and Lebesgue status measures. Okay, this is a fancy name for something that you already know. Okay, so these are just the random elements. The way you think of them is a ways of pushing the probability, in this case, the normal distribution from the reals onto the space. And how do you integrate with them? This is the the Riemann status integral. So if I have one of those measures and a function into 0 infinity, I do the precomposition and integrate according to the normal distribution. So that's straightforward. Okay, but when I say I read papers, semantics for basic programming, and very often this is what people do. Let's say, and then you have to show that everything is measurable. You don't actually have to do that. You just pick up the theory. It's all down there. So I kind of encourage you that if you need a foundation for doing something like this, then please use quasi-Borel spaces or do it in any other foundation. But repeating this for every paper, that's just a way of introducing mistakes. Reuse that. This structure, and it's very, very pleasant. Great. So even talked about probability. I'm very, very happy about that. I'll probably not get to it later. The last bit, so we talked about the right adjoint, limit structure. Now let's talk about subspaces. Then we have the full set for limits. Subspaces. So if I have a quasi-Borel space A and a subset X, then I get the subspace consisting of the points in that set and a measurable function for casting. Okay, so we're really trying to form this as a type theory, because when you do the proofs, if you stick to the type theoretic presentation, you don't have to check any measurability. It's really, really pleasant. And it really unroots some mistakes that otherwise are very easy to miss. Okay, so let's look at it. So what's the methodology of the subspace X? These are all the random elements that factor through the subspace. Really, really, what else would you like? Okay. So For example, say I talked about a two-dimensional sphere in space. This is the one-dimensional sphere in the plane. All the points on the unit circle is a quasi-Borel space. Automatically, you just write it and say, that's like what you do in measure theory. Improve the Skorokhod representation theorem. Doesn't say much, just says that you can represent the Steltes measures as CDFs. And that's just a fancy way of calling this theorem. Okay, so given a Steltes measure, you can represent it as the cumulative density, cumulative distribution function. Okay, just integrate from minus infinity until the point x. Okay, it's going to give you a function that gets 0 at minus infinity, 1 at infinity, and is cat-like and monotone. So cat-like means continuous on the right and has limits on the left. Okay, and from the left to the right, it's given by the integral, so it's obviously measurable. On the right, you have to define it using a supremum, but you already showed that supremum is measurable as well. So you don't really have to check it's an isomorphism, you just have to define it and show it's bijective. It's really nice. Okay, and this is inherently high order. I could not do it in measure theory, not like this. Another thing I can do now is talk about events. Okay, so I have events in a quasi-Borel space. Remember, I needed we have to measure events. So what is an event in a quasi-Borel space? It's a subset. Sorry, this should be an X. Yes, this should be an X, and this should be an AX. I alpha converted incorrectly. Okay, so this is a subset X, such as for every random element in A, the inverse image of X is a Borel subset. That ends up being a sigma field. And moreover, using characteristic function, it's in bijection with the quasi-Borel space both measurable maps into two, just like in mesh. But unlike mesh, I can form the exponential. Now I have a space of events. So I can talk about random events. And some use it, well, negatively. Using results from distributive set theory, you could show that if you look at the Borel on Borel, some of them don't exist. Sorry, Dario. Sorry. Sam, Dario, and Michael, and Martin. Sorry. That's why there's a reference. Thanks. To rule out some behaviors, right? Something, if some axiom of name generation doesn't hold, then I would get a Borel subset, and that subset we know doesn't exist. Therefore, that axiom holds. It's very cool. I really recommend you read that paper. Well done. In his PhD, right? It's pretty cool. And Michael's master's thesis. Okay, great. So we have now the space of events. We also have the scale of events, and that gives us a measurable space structure for every quasi-Borel space. And that gives us this adjunction I mentioned earlier. And you can maybe tongue-in-cheek slogan: every measurable space is carried by a quasi-Borel space. Right. So I can work in quasi-Borel spaces if I just say I'm actually measurable or not just quasi-measurable, then I'm recovering the old theory, but I can get more spaces if I give that up. More spaces, more functions, more fun. Okay, so now I come back to what I promised is why do we not contradict Aumann's theory? How does everything here fits? Okay, and it's this little picture. So by generalities, I have both the measurable space over the exponential times x, and I have the measurable space over the exponential times r. Sorry. So I can form this product in quasi-Borel spaces and take the measurable space over that, the free one, and I can take the measure space over the exponential and take the product in mesh. And these are different. These are different spaces. And the evaluation map goes from here, but it does not factor through here. That's Aumann's theory in this diagram. Okay, so the products are different. I have more measurable maps. As I said, more fun. Okay, picture says it all. Thank you, diagrams. Any questions on this?
You philosophically thinking of measurable spaces like as QBS is a bigger.
Algebras over QBS. This is for me what the picture says.
No, but is the case that one of the things is supposed to be like embedding into the other? I know it's not like that exactly on the node.
That's in the last bit. We'll get there. So this is the second part of the talk. I'll go to the third one actually. I think it's going to be okay, but I can always just hit the panic button and it's going to be okay. The last thing I want to do, there's a clock there, so I'm set. your coffee is safe. Okay, so I'm not going to do more probability. As I said, there's a course. I will show you a bit more of this, how it gets rid of measurability, even though measurability is still there in the background, like Alex and Chief atomic sheet proposal, which just really gets rid of it. Okay, so first ingredient is a Borel embedding. So what's a Borel embedding? From A to B. Well, when you take the image, you get a subspace of the following. B. And what you want is that the morphism is actually an isomorphism between the source and the image, like we do in topology. It's a natural definition. So the embedding E is when the image is isomorphic to the source through that function. For example, the set of all subsets of the reals that are Lebesgue now is a Borel subset, because you can just integrate them and get 0 and check whether it's 0 or not. Therefore, the subset is a Borel embedded into the reals by the identification. These are not Borel subsets. I don't want you to feel like everything is rosy. Okay, thanks, Dario. Okay, so I cannot. So the significance of a Borel embedding is I can test whether I'm in the subspace or not. Right, so you can view it as some kind of a measurable tester. You can do an if then else, and it gives me a theory of partial functions. But this one I can't check whether a random set is empty. I can't check whether it's one random set is containing another one in a measurable way, and I can't check whether it's open. I can restrict myself to the subspace of opens if I somehow establish that what I get is a subset through different means, but I can't test it measurably. The point of that definition was to give this definition. A standard Borel space is a quasi-Borel space that is Borel embedded in the reals. And that makes it a very nice space. So the slogan is standard, is concrete, is well behaved. It's like the data is standard. Functions are abstract. They learn this way of abstract, but what abstract is. And now to answer Nick's question, if we restrict from the measurable spaces to the standard Borel space, this definition also works there, where you talk about an embedding of measurable spaces. And it works for quasi-Borel spaces, and the subcategories are the same. So in that sense, quasi-Borel space is a different extension of the nice case. It's a nice extension of the nice case. It's pretty neat. That answer your question, Nick? Yeah. Great. So I'm now 10 minutes before the end. I'll let you ask some questions, so I'm going to continue, but I will not go past 5 minutes before the end. Okay? That's for you, Chair. So, because I think it's a compelling use case for just getting rid of measurability or hiding measurability, extracting all of it. Okay, so the classical theory, what do? You define some space, and in order to define a space, you have to define a signal field. Then you want to show some operations are measurable, but then you need to show that some events are measurable. That requires you to know something about the signal field structure, so you show it standard. Okay, so usually 1 and 2 come together, you define some metric, you show that it's separable, that it's complete, and then you can show that the operations you care about are measurable. Here you can actually start at the end. Because we have more spaces, because we have more types, type combinators, we can define the space, a data structure, that supports the operations you care about. It's there. It might not be concrete. So then you can show it's concrete. And if you really care about knowing exactly what all the events are, then you can build a metric and show that it's separable and so on. So you flip it, and it's more like a pay-as-you-go. Okay, if all I want is a space, I can just use the space. If I want the standardization properties, because they have lots of them, okay, then I can show it's standard, but I still don't have to find a complete separable metric, which is a pain in the neck. So let's look at this as a use case. I'm going to finish with this, and it's going to take me less than 3 minutes, Chair. Oh no, you can ask some questions. So let's look at a simple example. This is a well-known result, apart from the last little bit at the end. The uniform convergence space. So this is the space of continuous functions, well known to be concrete. We're going to show how that proof looks like with this meta theorem, with this foundation. So first, let's just define the space. This is going to be the subspace of reals to the reals, consisting of all the continuous functions. There we have it. We have it. We have a space. Okay, everything is well defined. I have evaluation because I can pass the function and apply it. Everything is measurable. I can even abstract, but then I have to show it's continuous. So now it depends on whether I'm showing it by hand, I'm showing it with theorem prover. I can do it in different ways. But once I do, I can form now that function as a function in the space of continuous functions. And because internalization and externalization is so smooth, this is actually not that horrible. You can do it by hand. It would be nice if you can do it automatically. With the meta theory that's working. And I know how to do that. Okay, that was step one. We now have, if we never need to know that it's standard, we can stop. We don't need to work out. Next, prove that it's standard. So now, we're thinking about this maybe descriptive set theory in the informal sense. Okay, we want to find a code that represents all the elements of the space uniquely. If we're trying to encode that function as a data type, okay, then we're going to take the space of codes to be a subspace of rationally indexed sequences of reals, like an infinite vector of reals. Okay, it's going to be all those sequences that describe a continuous function. Okay, and the basic idea here is that being continuous on the reals is the same thing as being uniformly continuous on every closed interval because of Cantor's theorem, Bishop continuity. It's called a constructive setting. Okay. And this condition being uniformly continuous is something I can check. With the predicate, you have to read it. It says for every interval, for every epsilon, there exists a delta such that if you delta close, you epsilon close on the image. And if you do it on all the rationals, it extends to all the reals. And that's why this is the right collection of codes. And now we need to build an isomorphism. Okay, so in one way, we just restrict the rational values. On the other way, we just extend, right? So find a rational approximation of the real you get, and then calculate the limit of the sequence. And this is a term in the language, so it's measurable. I don't have to check anything, because I gave myself a little programming language for measurability. So I need to check this, and it's a bijection, right? It's bijective. It's surjective and injective, but I can do that. And I'm done. It is now standard. I'm going to take 1 more minute. If I really cared about events, if I really want to know how do I get all the events in this space, then I need to work out. And really, this is everything you do in step 1 in the classical story. Okay, so here's a little theorem, or working towards a theorem. So a few concepts. So a metric on the points is compatible when it's measurable. So I have a quasi-real space A, I have a function that's a metric. I say initially it's compatible when it's measurable. And the topology generated by this measure has measurable limits if the space of converging sequences is a Borel set, is an event. And taking the limit of a sequence, so I'm guaranteed it converges, or I can also check it measurably. That's also a measurable function. Okay, that's theorem. If I have a metric that is A compatible, so it's compatible with the quasi-Borel space, and it has measurable limits, and it's separable, then it generates the events. It looks like it doesn't have enough information, but it does. I can show you the full picture. It's neat. And that's because showing these conditions amounts to doing all the hard work you usually do when you want to construct a separable, complete metric. Okay, so here's the full proof. Defining it is defining the uniform metric on this space. I can do it by calculating on the rational points. That's measurable. Checking that something converges because it's a complete metric amounts to checking it's a Cauchy sequence, which I can also do measurably. Okay, and the being separable is something you already know using Weierstrass's approximation theorem. And there you have it. That's the full proof. And you can do the same thing for the Skorokhod space, which is a lot more complicated, but the same recipe works. And I'm currently looking, I promised I'm going to tell you what I'm currently looking at. I'm looking at the Efros space. Okay, and the Efros space is of a Polish space is a measurable space structure over its closed subsets. And if you look at the Efros space of L2, that gives you a representation for Polish spaces. So I can have a Tarski universe of Polish spaces. So I can talk about do metaprogramming for topology. Okay, for continuous solutions. So looking at that, but I'm not going to say more than that. tell you offline. And that's it. I'll stop here. We talked about what is a methodology in quasi-Euler space structures, quasi-Euler spaces. We talked about the simple space structure. I've shown you how to use them. This kind of simply type measurability by type checking. I didn't tell you a lot about the quadratic structure and probabilities. Didn't tell you about the pen type structure, which I didn't tell you offline, and about spares of random variables and processes. And many more technologies. So I'll stop here. Still on time. Take more questions. Thank you.
Thank you so much, Ohad. Being so nice to the chair. I mean, actually, the easiest job. Oh, and even the first.
So, you mentioned early on in your talk, examples of Italian.
Yes.
That says that a certain something doesn't exist in classical set of the reactive choice.
Yes.
Does that certain something exist uniquely inside QPS? If you interpret the reals to be
Yeah, because
with that,
because it's a standard Euler space, so it exactly coincides with the usual theory. So on the real, it's fine. Yeah.
and is that object R with its QPS structure, is that actually the real number object?
Oh, internally. Alex nods vigorously, so I say yes.
That's cool. Good.
I can make sure those places we have video and have to do that.
Yeah, yeah.
Would you say that it's how we create the methodology?
Yeah. So I'm using, so there's two things. So I can do the Geary thing. I can take just a collection of measures and equip it with a methodology that basically says evaluating a fixed event, right, is measurable. That's not so good. And like the Geary, it's not even shown, I think. I have not done that. It's fixed. So for every event, you can evaluate that event. I don't think that's going to be shown. For measures, not probability measures. Okay. You can do a bit better. You can say the probability function, the measure as a function is measurable. That gives you another kind of Geary monad. But actually what worked a lot better is to take S-finite kernels. Okay, we've done that in the paper. That's a bit more involved, but what you do is you take the Lever-Extaltes measures and you quotient them by law. So two measures are the same if they have the same law. Okay, and that's the one we use, and that's really good. That works really, really well. That answer your question? Thanks. So I guess maybe taking away, it's not just one thing you can do 3 things. Okay, if you want to do in counting. Yes.
Thanks, Ohad, for the very cool talk. So I know nothing about probability, and I just wonder if say I wanted to, for instance, learn things that you might expect to learn in undergraduate probability, and I chose to do it all in QBS instead. Would that work, or would I get stuck, or what is QBS bad at, if anything?
So I'm going to give you the tongue-in-cheek answer, and offline I'm going to give you another answer.
Okay.
So the tongue-in-cheek answer is I had an undergraduate student. They did probability of an undergraduate, but then didn't do measure theory and so on. They went and did a project with me on quasi-Euler spaces. They're now doing a PhD in statistics. So does that answer your question? So maybe you take so continuing tongue-in-cheek, Nick. If you take a course. No, if you do a measure theory course with me, you're going to do it, yeah. But maybe not with other people. So, I'll answer more later. I think it's we're hitting the break. Unless there's any other question.
Yeah.
Yes.
There's a couple places where you use the reals as a standard prototype of a standard graph space.
Yep.
Could you use any others?
Any uncountable standard space, yeah. They're all homomorphic. And some use them for lazy people.
That's exactly what
Yeah. In fact, sometimes it's better to use like unit intervals because it's a bit more intuitive, but it doesn't change the category.
Great. Well, thanks so much again.